Howdy folks, Coach Primo here. This is SAS 4 lesson, Road to $1 Million. We're going to look at how to determine how much money you need to initially invest in order to have $1 million after the investment matures. And what that means is, as long as you know what the interest rate is bearing per year, how long you're going to keep that investment, and how many times it's compounded per year, you can determine how much money you need to invest now to have $1 million in the future. So let's take a look and see what that looks like. All right. So the Bellringer is, if you knew how much money you need to retire, is there a formula that can calculate the amount of money you need to invest now? How would you use that formula, and what would that formula be called? Before we do, let's talk about great things. So what's some great things? I feel like I'm starting to come into my own. I'm starting to build more garden beds. Going to go get some more dirt and put some more stuff in the ground. You know, there's a great feeling of accomplishment when you get your hands in the dirt and you plant stuff, and you know that in the future, as long as you take care of it, it's going to bear fruit. I mean, pardon the pun, but that's the truth. I'm going to end up putting stuff on my table, and all I had to buy was the seed and the dirt and the stuff to build the beds. So, you are welcome to share things that are great for you. I trust and pray that everything is blessed with your life, and that everything is going good and you're sheltering in place, staying healthy and keeping your hygiene up and taking care of your families. If not, please reach out to me. I'd like to hear if there's anything that I can do. Lesson objective. I can use the time value of money formulas to make investment decisions in real world situations. Okay. In the last lesson, we analyzed the future value of an investment over time. We began with $2,600 invested into a savings account for 30 years. And after 30 years, our initial investment would be $9,062.70. Well, in this activity, we look at the same investment in a different way. Question relates to the time value of money. What is that $9,062.70 future value worth at various times in a 30-year investment? So let's look at that. So this table that we're looking at looks very familiar, but the first column isn't how many years. It's not 0 to 30 from 2,600 and 9,062. In this table, the 30-year investment is the one you've already explored, but the other values in the table show you how much principal you would need to invest and length of time the investment for the same yield. This can be thought of as a present value of the investment. So, for instance, say you wanted $9,060.70. How much would you have to invest right now to have that much? You'd have to invest exactly that amount, $9,062.70 right now, 0 years till maturity. What if you wanted to wait 5 years and you knew what the interest rate was? Well, you don't know what the interest rate is, but you know that the principal required is $7,359.95. If you're going to want $9,062.70 in 10 years, you'll have to invest this amount. In 15 years, you'll have to invest this. 20 years, this, and so on to 30 years. If you want $9,062 in 30 years, at that particular interest rate, whatever it is, you would have to invest $2,600. Okay, so let's create a scatter plot and label the axis and scales. I've done that for you already. So the principal required is this column right here. That's how much money you have to initially invest. And this is the time until maturity. So at 0 years, you'd have to invest the $9,062. In 1, 2, 3, 4, 5 years, you'd have to invest that much, and so on. So it's still an exponential curve. Notice that it lowers a little bit less every year. This is the value that you would presently have to invest to have a certain amount in the future. Does that make sense? So calculate the regression equation for the given data and graph the regression equation on the scatter plot. As I've said before, you can use an online emulator that will emulate or copy exactly what the TI-84 Plus does that we have in our classroom. I'll leave a link here for you to go to and get it. Know that if you get that emulator, you'll have to sign up, which is fine. You put yourself down as a student. Shouldn't cost you anything. Okay, so Let's take a look at what that is on the calculator. So we'll back up to the table. And this year, this years to maturity is going to be L1, and the principal required is going to be L2. Of course, we want to turn on scatter plot, so let's do that. Turn it on. Enter, enter. And we're back there. I'm going to go stat, enter. Okay, so L1, that's an easy one. So now I have L1 is from 0 to 30 years. And now I have L2 as the principal required in L1 number of years to maturity. So I didn't even graph it, did I? Let's zoom 9, see what it looks like. It looks just like the one that we had in there, okay? Stat, calc. We'll go to exponential regression, which is 0. You can actually click 0. It'll do the same thing. We put L1 is the years to maturity in that column, and the L2 column has principal required. So we'll just enter through that until we get to calculate, and it calculates. And we have our answer here. A is 9,062 and 68. Notice the 68 cents. The 68 cents is not the same as the 70 cents. It's just a little bit off. But this is the factor we're looking for, that common multiplier, that ratio, the ratio of 1 year to the next. Notice that wouldn't be the interest rate. It might be, but that's the change. Yeah, it is the change every year. That is, the interest rate would be 100 minus that, or the complement of this. So let's take a look at what that looks like now. And there's our regression formula. Look, it even has a 68. But here is that value that I was talking about, the common ratio or the common multiplier. What are we multiplying this amount by every year? X is the number of years, and Y is the value of the account in so many years. The present value, if this is the future value. And we'll talk about that here in a second. There's your curve, nice and pretty. You're now a financial consultant, and your first client is Josephine. She is 20 years old. She wants to save $1 million for retirement in 50 years. So 50 years from now. So if we're looking at this future value formula, guess what? T is the number of years. We have that written down here. Assume she invests in a savings account that earns 3% interest, and determine how much Josephine must save to reach her retirement goal. Okay? So notice that we did not use anything for the compounding periods because it just says a savings account that earns 3% interest. If it doesn't give you a compounding period, we assume that it's annual compounding, okay? So Josephine does not want to begin saving for retirement immediately. We're going to fill in this table to show the amount of money she must invest to retire 50 years from now with $1 million based on the number of years that she wants to wait to start saving. So we use the calculator to do this, and we're going to use that formula we calculated here, this 1 million divided by this. So if the future value is the present value times this amount, the present value is simply the future value divided by this, okay? So notice that we said that in 50 years she has to have just to invest $65,584 and some change. You get the idea that you can make $1 million by leaving the money in there for a long time. Well, that's true. And if you have that kind of disposable money hanging around and you got 50 years to wait, awesome. Well, for me, that doesn't make sense. I'm 53. I wouldn't be able to see that $1 million until I'm 103 if I make it that far. However, if I want to put it into a trust for my grandchild or for my child, it could wait 50 years and they could get it when they're 60 and retire, and they would have $1 million. Yeah, so let's look and see how much would she have to invest if she only wanted to wait 0 years. So in other words, she wants $1 million now. She wants to start saving in 0 years. She only has to put $228,107 in. If she's going to wait until 10 years go by to start saving, she has to put $306,000 in to start. She wants to wait 20 years. Notice that it increases more and more until you get to the 50 years. If she wants $1 million in 50 years, but she's not going to start saving until 50 years from now, she's going to have to put $1 million in. 30 years, she'll have to put $553,000. And 20 years, $411,000, almost $412,000. You get the idea. The longer she waits, the more money she's going to have to put in. So it says if she believes in spending now and saving later, how could the table be used to convince her otherwise? So you can easily determine that the longer she waits to start saving, the more money she's going to have to put in. So if she starts saving right now, she only has to put less than $250,000. The longer she waits, the closer it is to $1 million. If she waits 10 years, she's going to have to put in another almost $100,000. 20 years, another $100,000. 30 years, another $250,000. 40 years, another $250,000. And if she waits all 50 years, she's not really saving any. She's not making any money with her money. She's just putting money in the account. What for? So she can spend it. The longer she waits to save, the more principal is required. The more present value is required to make that much money. Next client is Blaine, who wants to have $1,000 in 10 years. The following 3 accounts are available for Blaine to invest in. The first account is a savings account that earns 3% compounded quarterly. Second one is a checking account earning 1% compounded monthly. The last account is a money market account earning 4.5% compounded semi-annually. Plans on making no withdrawals or deposits for 10 years. Now let's rewrite the future value general formula for present value and allow for any compounding period. N. Okay. So notice in the earlier one, the future value was a present value times this amount. But the present value is just the future value divided by this amount. This is the general formula for the present value of an investment. So we're going to rewrite the present value formulas for each account that Blaine is considering, and we're going to make sure that the formulas include compounding periods other than annual and incorporate the different rates. So this is the checking account that has 1%, okay? 12 times T. T stands for the number of years. So he wants $1,000 in 10 years. What we did here was we divided the annual interest rate by the number of months, added it to 1, and then we multiplied it by 12 times the number of years, because that's the total number of compounding periods through the life of the loan. The number of compounding periods times the number of years is the total number of compounding periods throughout the life of the investment, through all the years. So if it's monthly, it's 12 times the number of years in this case. In the savings, we have a 3% interest rate, compounded quarterly. So we take that 3% in decimal form, 0.03, and we're going to divide it by 4 and add it to 1. And then we're going to raise that to 4 times the number of years, 4 compounding periods per year. And then we're going to divide that into 1,000, which is the future value that we want in the investment. Finally, the money market account is 1,000 divided by the 4.5% interest semi-annually. So it's 0.045 divided by 2. And then we're going to add that to 1 and multiply by 2 times the number of years. So the total number of compounding periods is, since it compounds 2 times a year, we multiply that by the number of years, and that gives us the total number of compounding periods. So graph the present value formula for each account and label the axis, scales, curves, and provide titles. Now, making a graphical display of the way the money grows over the course of time really helps us determine which account is best suited for us. Notice that the checking account, the longer the time goes, it takes a lot more money to grow to $1,000. The savings account has a little bit better interest rate. I think it's 3%. And so we don't have to put as much in the course of 10 years. That money market, man, it's all the way down here to about $650 to make $1,000. So in 10 years, it'll make more money than the rest of them. So you have to invest less to actually earn the same amount. So which factor is the most significant effect on the curve, the interest rate or compounding periods? So the checking account has monthly interest rate, right? But it has 1% interest. Savings account has quarterly, but it has 3% interest. And a money market has semi-annually, but has 4.5% interest. And you notice it makes more, or it takes less money to invest initially to make as much money. So interest rates have the greatest effect. It's very obvious. The compounding periods are not as valuable as the amount of the interest rate you can get from the account. So which account should recommend Blaine to invest in? That's obviously the money market because it has the lowest principal investment required to make the same amount of money. I'm going to launch you with this. Wealthy people stay wealthy because they act like they're poor. Poor people stay poor because they act like they're wealthy. Now, you need to think about that wisdom before you start making decisions with money you earn. Because if you can't use your money to earn more money, then you're not doing your money right. I'm sure your parents or any of your older, wiser friends, aunts, uncles, they probably got some good wisdom, and your grandma and grandpa probably do too. So you might want to talk to them and see what they would say to do with your money in order to have your money earn money. Anyway, that's the end of the lesson. Be sure to answer all the questions if you haven't already, and be blessed and be a blessing.